Hello and Assalamualaikum to our panelists and viewer for my video presentation. This video is in purpose to present about my final year project MEC602 with a project title of Analysis of Internal Flow and Performance of Conical Converging-Diverging Rocket Nozzle at Various Atmospheric Pressure. My name is Siti Aisyah Syakirah Binti Hassan and I will be the presenter of the video. My supervisor is Ts.Dr. Ahmad Hussein bin Abdul Hamid and my co-supervisor is Professor Madya Ts.Dr. Zuraidah Binti Salleh. Do enjoy my video. Project summary. This study is focusing on converging-diverging nozzle. The converging-diverging Siti nozzle can convert pressure energy from the heat energy and fuel flow into the high exhaust velocity of kinetic energy. It transforms the combustion chamber's high temperature, high pressure and low velocity gas into low temperature, low pressure and high velocity gas. The present investigation seeks to evaluate the internal flow and the performance of Siti rocket nozzle at sea level condition up to 30,000 meter altitudes. Internal flow and the possibility of the shock development within the diverging region of the nozzle will be visualized using computational analysis. The analysis are run on the open-form software. The behavior of Siti nozzle is analyzed to understand the effect on different altitude on the flow structure, exit condition, and the performance of the rocket nozzle when the back pressure is reduced. Introduction of the project. The nozzle is commonly used in certain varieties of rocket engine nozzles and steam turbine. It is used in practically all current rocket engines that use hot gas combustion. To maximize thrust output, the rocket nozzle is responsible for controlling combustion pressure and accelerating combustion gases. Its operation is based on the properties of subsonic and supersonic gases moving at various speeds. Because the mass flow rate is constant, the speed of the subsonic gas flow will increase if the cross-sectional area of the nozzle reduces. The flow will be further accelerate in the diverging section of the nozzle, provided that the throat is choked. The nozzle utilized in a rocket with a wide Mach number capability present the most significant design challenges. Identifying the aspiration location is crucial for the rocket engine design because it determines the highest feasible nozzle area ratio, which is determinant of the engine performance. The area ratio of the nozzle can be calculated by dividing the exit area of the nozzle by the area of the throat at the divergent region. It was necessary to estimate the nozzle exit area ratio in order to assure that it will be capable of producing maximum thrust in the rocket at high altitude. While ascending from the ground to high altitude, aerospace launch vehicle face a continual shift in the ambient condition. The entire performance of the propulsion system is largely determined by the engine nozzle's performance characteristic at design and under a wide variety of off-design operating situation encountered throughout the flight. When the operating conditions of a Siti nozzle are too different from what it was designed for, serious performance losses occur. Predicting the separation position is really important for rocket engine design because it decides the highest potential nozzle area ratio, which is a determining factor in engine performance. Therefore, this study aims to analyze the performance and the internal flow at various atmospheric pressure and altitude. The ratio of the specific heat constant, the area ratio, the length of the nozzle, the divergence nozzle angle, and the pressure ratio are all the factors that influence the nozzle's performance. The data that need to collect is the flow condition and the exit condition as the decreasing in pressure ratio. The data also needs to be observed through the aspiration location. Literature review. There are 4 sections in literature review which are altitude compensating nozzle, divergent angle, nozzle area ratio, and the comparison of the conical nozzle with a bell nozzle. The altitude compensating nozzle such as a bell nozzle, aerospike nozzle, and expansion deflection nozzle are often compared to a matched ambient pressure or perfectly expanded exit symmetry nozzle. As a result of the preceding development, the perfectly expanded nozzle is the inaccurate benchmark and such comparisons are deceptive and useless for flight conditions. The peak thrust minus drag of the nozzle must be used to evaluate its performance. The term of thrust minus the drag is known as the excess thrust and also a vector quantity. It must be emphasized that if the rocket is taking off from the static condition, the maximum lift of acceleration for a particular lift of mass is determined by the area ratio that corresponds to the ambient static pressure. However, once the system is in the operation, the parameter relevance is thrust minus drag. Divergence angle of the nozzle. Divergence section will be dependent on the expansion ratio and thrust needed, which correlates with the ratio of the exit area, which can be varies based on the divergence angle. From the figure, a divergence angle beta are able to be observed. To assess the impact of adjusting the divergence angle on the nozzle's internal performance, research have been conducted for several Siti nozzles with divergence angle ranging from 7 degree to 50 degree and nozzle area ratio ranging from 1.29 to 3.81 over a huge assortment of nozzle pressure ratio. At the pressure ratio where the separation occurred within the nozzle, the thrust coefficient was reduced with increasing the divergence angle. For a nozzle that having a given expansion ratio, pressure ratio, and operating with a separated flow, the separation point occurred closer to the throat for the high nozzle angle, thus relieving overexpansion losses. Therefore, at pressure ratio below design, the nozzle performance improved with an increase in divergence angles. At any given divergence angles, a change in expansion ratio had a negligible effect on the nozzle performance at the design pressure ratio. Although the divergence angles and expansion ratio were found to have no effect on the nozzle flow coefficient at choke pressure ratio, the pressure ratio required to choke the nozzle is increased with an increase in divergence angles. Nozzle area ratio. The section area ratio of the exhaust nozzle must be controlled to limit the flow separation phenomena in the diverging part of the exhaust nozzle at sea level. As a result of this constraint, the performance suffered at high altitude. A continuous adjustment of the expansion ratio with employing a changing geometry nozzle will be an ideal response to the adaptation challenges. Increasing the nozzle area ratio of satellite launch vehicle to achieve the best expansion during the operation can provide up to 20% thrust augmentation at low altitude. The profitable and practical approaches for improving the area ratio of high-altitude nozzle with shock-free nozzle control on the launch vehicle will allow for a higher payload potential than the conventional one. When such flow is from a converging nozzle to a suddenly expanded circular duct with a larger cross-sectional area than the nozzle exit area, it is discovered that as the NPR tends to increase, the impact on the base pressure is marginal for NPRs up to 2.5. Nevertheless, at NPR 3, the base pressure drops dramatically and the viscosity accounts for the momentum loss. It has been discovered by selecting an adequate length of axial clearance, the nozzle-rotor interaction losses can be reduced. If the grid quality is poor and the flow around the stagnation location is higher, the CFD model will not converge. Comparison of a conical nozzle with a bell nozzle. A direct comparison of a conical nozzle with a bell nozzle optimized for maximum thrust using the round method was undertaken on two small rockets, which is 110 Newton thrust class. The bell nozzles outperform the conical nozzles on big rockets with a throat Reynolds number larger than 1 × 10⁵. However, test findings for rockets with a throat Reynolds number less than 1 × 10⁵ have been equivocal. Based on a recent study, two small nozzles were tested at 2 different full flame cooling percentage and 3 different chamber pressure in an experimental investigation. The bell nozzle outperformed the conical nozzle in the throat Reynolds number range of 2 × 10⁴ to 4 × 10⁴ according to the test dataset. The bell nozzle had slightly greater thrust coefficients than the conical nozzle, ranging from 4 to 12% higher. On the other studies, lowering the fuel film cooling improved the performance for both nozzle types, as predicted by the researcher. Problem statement and objective of this research study. In response to the increased demand for improved performance in rocket launcher, the development of better nozzle is being encouraged. The majority of the time, this is performed by raising the expansion ratio. However, this may result in flow separation, which may place the nozzle and the other engine components at risk of exceeding their lifetime limit. Firstly, the current research is to analyze the performance and internal flow of various rocket nozzles at different altitudes. Then, this project aiming to find out more about the effect of ambient pressure on the flow condition inside the nozzle. Additionally, the purpose of this research is to determine the location of separation in the flow inside the nozzle and to increase the maximum efficiency of the rocket nozzle. The scope and limitation of the project. By analyzing the flow condition inside the nozzle, the study precisely analyzed the nozzle rocket's performance at various altitudes up to 30,000 meters with a 1,000 meters increment. There will be 5 cases evaluated, each with a different error ratio of the nozzle: 4, 5, 5.29, 6, and 7. Each case has 21 specimens from various altitudes. This research includes approximately 105 cases. Additionally, the separation point within the nozzle must be evaluated. The study will be conducted through the use of computational analysis, more precisely through use of a Java applet program, and using an open source solver, namely OpenFOAM. The methodology of the project. The flowchart represents the overall process involved in this project is depicted in the figure. For the objective managed to be realized, is it necessary to follow the entire process from beginning to end? The project will begin with a lot of literature review, which will fill in the gaps necessary to achieve the goals of the analysis. Even after the data has been determined, the information from the literature review is essential in order to ensure that the theoretical data can be compared to the result of the CFD simulation. To guarantee that the objectives are achievable, all the data acquired for analysis will be collected, validated, and compared with one another. The CD nozzle with various area ratio operating under various nozzle pressure ratio (NPR) were first analyzed mathematically using exact solution. The solution assumed that the flow is steady, one-dimensional, and behave as an ideal gas. Furthermore, the flow is assumed to be expanded isentropically, and that the Rankine-Hugoniot relations are used for normal shock wave in perfect gas. The mathematical analysis allows us to have a complete understanding of the general characteristic of the design and is used in the early design stage before turning it into a real product by employing engineering principles that are crucial to the product development. Furthermore, by conducting such an analysis, is it possible to gain a rough grasp of the internal flow and the performance of the rocket nozzle with a greater ease. Result and discussion. Initial finding. Using all the mathematical modeling equation and with the help of Java applet program, I managed to tabulate the data for this research presented here. I've been illustrating the finding in the separation location graph. The separation location can be identified when there is a sudden drop in Mach number. The separation points only happen until 3000 meter altitude at error ratio 7. The separation does not happen beyond that altitude because non-normal shock occurs in the nozzle when the bed pressure decreases even further. The jet pressure feeds the bed pressure via oblique shock wave outside the exit plane. There are only one case of having normal shock wave at error ratio of 5, 2 cases of error ratio 5.29, 3 cases at error ratio of 6, 4 cases at error ratio of 7. These cases experience normal shock wave in the diverging section of the nozzle. The rest flow condition will be either overexpanded or underexpanded as the bed pressure decreases. Therefore, no flow separation happen inside the nozzle. When the pressure ratio is reduced until there is no normal shock wave formed in the diverging section of the nozzle, the exit condition will be consistent for lower pressure ratio. In order to verify the location of the separation points obtained through the theoretical calculation, the cases where the flow is separated from the nozzle wall are solved numerically in OpenFOAM software. There are 16 cases were simulated in OpenFOAM. From the simulation, 1 cases of case A at a ratio of 5, 8 cases of case B at a ratio of 5.29, 3 and 4 cases of case C and D with a ratio of 6 and 7 respectively. From the figure, it summarized the CFD result for the cases investigated. The theoretical data was also plotted in the figure for the sake of comparison. It is observed that the trend of the separation point with a pressure ratio for both theoretical and CFD result are in good agreement. This is due to the fact that when the NPR is increased, the location at which the flow near the nozzle wall is halted more further upstream, resulting in a longer region of separated flow. At the initial point of adverse pressure gradient, the flow separates from the nozzle wall. Once the fluid has disengaged from the surface, it produces a constant pressure on the surface rather than a continuously decreasing pressure if it is still attached. Generally, as the flow expanded in the divergent region of the nozzle, it spread from the nozzle wall at some axial location where the wall pressure reached a specific fraction of the ambient pressure. The separation point predicted by the theoretical value is relatively closer to the nozzle exit than those predicted by the CFD simulation. The general trend of CFD data observed in the figure indicates that there is still a shock wave occurs in the nozzle even in the lower range of the bed pressure. However, CFD solution predict a flow separation within the diverging section of the nozzle at this nozzle pressure ratio. This observation is likely due to the invasive assumption in the theoretical solution, while the viscous effect is taken into account in the CFD simulation. Is it also observed that the separation point moves towards the throat as the nozzle area ratio is increased while operating at the same NPR. This is somewhat expected since when the area ratio is increased, the drag and non-axial component of the gas velocity are also increased, which result in the flow to separate earlier. As the conclusion, internal flow of CD rocket nozzles with a variable area ratio and back pressure was evaluated and compared using theoretical and numerical data. Because the boundary layer is traveling against an adverse pressure gradient in some situation, flow separation occurred inside the nozzle. The velocity drops as the pressure increases in the direction of flow. The boundary layer's velocity eventually drops to zero, and it separates from the surface. The separation does not occur in the case of nozzle with an area ratio of 4 because it has a constant pressure, temperature ratio, and no sudden drops in Mach number at the exit condition. In comparison to the CFD result, the theoretical solutions predict a separation point that is substantially closer to the nozzle exit plane, which is most likely due to the invasive assumption in the simulation. The result also shows that as the area ratio increases, the separation moves upstream of the nozzle. A variable nozzle for the thrust chamber of the rocket engine with an improved expansion ratio was also provided during the rocket's ascent to a high altitude where atmospheric pressure declines. Lastly, low expansion ratio nozzles are better suited for low altitude application, whereas high expansion ratio nozzle are more suitable to high altitude application. That's all from me for the research presentation of final year project. Don't hesitate to ask me by drop your message if there's any question regarding this video presentation. Thank you.